What? We're rolling? Uh, Good morning. Today we will be doing our virtual field trip. I'm standing here in a mechanical room that I've turned into a makeshift classroom. Unfortunately, you will not be able to join me today, but had you come, you would be sitting in an actual fan mechanical room. Some equipment back there. And we would go and talk about a little bit of electrical safety, but mostly building distribution. And so that's what we are going to try to accomplish today virtually. And I hope that it comes across just as good as it would as if you were with me today. Before we get into that, I'd like to just give you a little tour of my building so you have a better understanding of what it is I do all day long, which is basically nothing, as you'll come to find out. Come on, let's take a walk.
Once known as Chicago Place, was an 8-level specialty retail center created to recall the elegance and intimacy of Chicago. It is located at 700 North Michigan Avenue in the heart of the prestigious Magnificent Mile. Designed by Skidmore, Owings, and Merrill, the building's rich textures, colors, and large display windows created an exciting impression for shoppers. The center, completed in 1990, comprised of over 500,000 square feet, contained over 310,000 rentable square feet, topped with food court that once featured 9 restaurants in an atrium garden setting. The building facade combines granite, limestone-colored precast concrete, stained and vision glass in a manner that honors the city's rich architectural heritage. The building is served by a dual medium-voltage electrical service, including open transition transfer switches, connected to a 750-watt cat generator. Now back to my daddy for your field trip. I hope you enjoy.
Okay, we're going to go up to the 8th floor, which would be the top floor for retail, or what was retail back in the day. 8th floor was home to food court, a massive food court that would have a lot of hustle and bustle around lunchtime, but other than that, it would pretty much be dead. And there was a couple other retailers that were up on this floor. But since the building was sold in 2005, all the retailers pretty much were booted out of here. So now what we have is pretty much a vacant mall for the most part, except for the 3 tenants that do occupy some space, which is Saks, T-Mobile, and Zara. Oh, nice little water damage from roof deck. Abandoned planters. Once was a beautiful water feature here at this fountain, all filled with water. With a little flowing river, a little bridge, you could walk over it. Little bubbler over there. Used to be really beautiful. There's our architectural headdress from the 80s. One day I'd like to use that as a headboard. Be a hell of a bed, but just for the memories. See all the dust on the ground and dirt. Nobody's been through here in 10 years. Mall officially shuttered April 1st, 2010. So, yeah, 10 years. So if you're familiar with Water Tower Place, we were very similar in that we had this open atrium concrete infill slab that you see down there. Below that is T-Mobile. It used to be just a lobby from Michigan Avenue that you could walk into the mall, take the escalators up and down, hit every single floor, do a little shopping. Let's take a little walk down. Afraid of heights? So about 45% of the entire building is sacks. Here's the curtain wall, and it basically goes and spans the entire building. So they have been always pretty much isolated from us. There was the ability to walk through, but as you can imagine, the people who would typically do their shopping at Saks would not come in and shop with the ma and pa retailers that Chicago Place was attracting at the time. Most of the floors are still built out, old storefront space. I'm gonna bring you down to this floor right below. It's the 6th floor. We demoed this entire floor just so potential clients, brokers, people who were interested in looking for space could get a better idea of the volume of space available here. Let's take a look down Michigan Avenue. That is looking south. The old Apple store. So here's what a gutted floor pretty much looks like. Turn on some lights over here so you can get a little bit better perspective. A little bit better. And the way the building is designed is, this is looking east toward Michigan Avenue. And if you remember from the still photo earlier, it showed that there's a tower above us that is part of this development. That is the 100 East Huron Condominium Associations. So the support system for the west half of the building is all concrete, as you can see, all concrete columns, whereas the east side is I-beam steel. The slabs are concrete slabs, steel deck, poured concrete slabs. So that's what we're walking on here, the concrete slab. Looking at the bottom of it, which would be the ceiling here. It's just the steel decking, corrugated steel decking, where they pour the concrete into it. Let's look out west, looking at Rush Street. If you're a fan of Giordano's Pizza, there it is right there. course, the world famous Rosebud, right on the corner of Rush and Superior. Show you one of our standpipes for the sprinkler system. Control valve. Zoom in a little bit. OSMI control valve. Tamper switch connected to it. Right off the discharge side of that is you will see a flow switch to monitor if one of the heads on this system were to burst. Let's find the head. There's a head. So if that head were to burst, water would be flowing through that pipe, and the paddle connected to that flow switch would be activated, which would then in turn send an alarm. Fire department would be on their way. So there's, I think at one point maybe 84 retailers that were in here, little small mom and pop shops that occupied all these inner floors. But the building really was not doing too good. We were losing anywhere between $2 and $3 million a year. The building was owned and managed by a developer who was basically into office space. So even though they did have a couple of retail holdings, they were managing this from Minneapolis. They're a Canadian company. And the people in Minneapolis didn't have a fucking clue what they were doing. They just, you know, markets are different, retail markets from municipality or big city to, you know, from Minneapolis to Chicago, totally different workings. So they didn't really have an idea, and I would say it was mismanaged. And so anyway, when this previous owner wanted to get rid of the property, they sold it at a deep discount to my now current owner, who had a different vision for this place, which was convert the lobby to retail space, charge the highest rent in the Midwest, which is what T-Mobile's paying. Zara, their other high-paying tenant, is on the corner of Michigan Avenue and Huron. And Saks, their biggest tenant, this just goes to show the mismanagement of the previous owner. Saks has a 50-year land lease, which means they pretty much own their parcel of the property. They've got a separate property tax number, so they pay their own taxes. Their taxes are separate. It's basically costing us, I should say my owner, costing him money for them to be in here. Their base rent for 45% of this entire space. So if you calculate the entire building's leasable space, 45% of that is occupied by Saks, and they are paying only $25,000 a month for all of it. Where in comparison, T-Mobile is paying somewhere in the neighborhood of $400 a square foot per month. And they have 11,000 square feet. So you round that off, you know, 444,000 a month. Calculate that over a year, you know, you're at what, 5 million? So quite a bit of difference. All right, we're gonna go and head downstairs, start at the ComEd vault, and we will start our field trip of building power distribution. All right, we're gonna start off by going inside a ComEd vault. This is not the main vault. Typically, you would never ever be allowed inside a ComEd vault without a representative from ComEd being with us. However, as you can see, the door is ajar. It has been broken for quite some time, which enables us to go inside and take a look around. Don't know if you could hear that humming. That is the flow of current. All right, what we have here along this back wall are the risers coming from ComEd. This is extremely high voltage, 12 kV, 12 kilovolts. Conversion for a kilo is times 1,000, so 12,000 volts is what is present at this particular location. From there, it goes to these transformers. So there are rows of transformers in here that are able to step down the voltage to whatever is necessary or what is required. Here we got a lot of 277 volts, so that would be the high leg Y configured transformer. This way we've got also Y configured transformers in low leg for all of our 120, 208 volt requirements. Just giving you a little information on this particular transformer, telling you how to tap it to achieve these different voltages. These boxes that you see here are the main fuses. This is all ComEd equipment. But if we look just on here on the fuse components, look what the fuse amperes are max at. 200,000 amps. 200,000. A lot of power. Here's one of our caution signs. Hey, stay out of here. There's another danger. Bushings may be energized. From here, once we step down the power, there is another room. So all of these wires then go through this cinder block wall to go to a switchgear room. So let's take a walk over to the switchgear room. All right, we're entering the switchgear room. We'll go back toward that back wall that butts up against the ComEd vault that we just came in, or came out of, I should say. So here's the cinder block wall, the other side of it. Here we see the conduits protruding through that wall, okay? Do that in a couple different locations. And from there, they come right into the switchgear. All right, switchgear, if you recall, is a high-powered electrical device that will be used to switch or interrupt the circuits in the building's distribution system. Switchboard is a panel or assembly of panels containing switches, meters, buses, and overcurrent protection devices. Now, these two terms are typically used interchangeably. So here we could see a meter for ComEd. This is how they would come in and read the usage. Here is an overcurrent protection device, ground fault. All right, so this is basically the last point for the utility company and the beginning of a building's distribution system. Now, switchgear is rated by the manufacturer for a maximum voltage and current output. So if we look at each one of them, this one is designed for 800 volts sectional bus, supply bus, 3,000 amps. What we're putting through here is 208, 120. Another look for some more fuse disconnects. You see these switchgear and panel boards all throughout this room here. In addition to dividing the incoming power, switchgear normally contains all the equipment that would be required to control, monitor, protect, and record power usage. So back in the day, I used to do some load shedding exercises, signed up through ComEd. Their monitoring equipment is in this panel. They would be piped into all of this switchgear, and on days when it would be extremely hot out, or they'd ask for load shedding because they wanted to make sure that they didn't crash their system, they would put a call into us. They would be able to monitor through this exactly how much load we're shedding. Then what we would do is start turning pieces of equipment off, or actually going to emergency generator and transferring power over to generator and just dumping ComEd for certain loads, just to help achieve whatever goal that we had agreed to upon with them. Okay, here's a good example of safety labels. I think when you go pretty much take a look at every one of these boards in here, you will see that there is going to be a safety label that is going to be prominently displayed. Safety labels are present everywhere, especially in these high voltage areas. The signal word used on these is what? Danger, right? We know what that danger signifies. It's basically telling us, hey, there are imminently hazardous situations which, if not avoided, will result in our death or serious injury. Okay, I had showed you in the PowerPoint during our discussion an incident that happened. Wasn't in this room, but you saw what was the result of that, okay? Working in these panels while they were energized. I mean, this specifically tells you, listen, turn off power supplying this equipment before working on or inside. It's telling you in no uncertain terms to do so. And the people who were working in that and got injured, or probably dead, I'm not sure. Well, they were doing it with it live. Grounding. Okay, so because this is the service entrance, this is where all the grounding is taking place. So all these conduits here are converging into this one splice box. From here, they continue down into the earth. Now, grounding can be accomplished in a variety of ways. the connecting of a ground circuit to a metal underground water pipe like in your residence was probably something you would be most familiar with. When you get into commercial applications, grounding includes the connection to building metal framing, concrete encased electrodes, or just a ground ring that is buried beneath the building, basically. All right, some old meter sockets. All these were removed at one point. Had a big argument with ComEd. This is their equipment, you know, these meters. So they own this meter, and if you look on your bill, there's a charge, a rental fee for having these meters. Well, this is just one floor, okay? And although there was quite a bit of tenants that were being supplied from this one floor, it is kind of typical of what we would find on a lot of the other floors. So when this building was built back in the 80s, we got a huge discount from ComEd if we did all electric heat. And when they were designing and laying this building out, there would be multiple meters for each tenant, whereas that really doesn't make sense nowadays. Nowadays, people would probably tend to minimize and go with the least amount of meters as possible. 1 meter per structure, right? Makes a lot, or not structure, but for each business, which would make a lot more sense. But they were charging us quite a bit of money. So even after these tenants left, we were getting bills being sent over in our name with all these charges. And my owner was like, what the fuck is going on? Why am I paying so much money for a vacant space? So when we looked into it, what we had found was all these rental fees and all these other fees. And so it was an ordeal going back and forth with ComEd in order to finally get them to remove these. And what it was they said, listen, the only way we'll allow you to do that is if you remove all the breakers, which they're all removed, okay, and pull back all of the conductors from the meter, right, all the way back to all the tenant spaces. We're talking, you know, hundreds and hundreds of conduits, hundreds and hundreds of meters, and thousands upon thousands of feet of conductor, which I gladly removed and scrapped. At the height of when copper was for bare bright, the big, thick, stranded conductor, plus I was bringing in so much, I was getting paid a little bit more than rate. I was getting close to $5 a pound for bare bright. I pulled probably easily over 100 grand out of this place. All right, let's step out of here. And this is where I have all my prints for all the old tenant build-outs, base building, main cover sheet, the index of drawings, landscaping, civil drawings, architectural, mechanical, structural, plumbing, and electrical. And on the electrical, as part of your electrical drawings, what you will have is your single line. Okay, it's your power riser diagram. It's also referred to. It is a single line, and here, this is a drawing that is, you know, part of your blueprints and uses the single line and basic symbols to illustrate the current path, voltage values, circuit disconnects, fuses, circuit breakers, transformers, panel boards, all that shit that you would find in a building's distribution system. So let's take a little bit closer look at this. All right, we'll start over here. Okay, so right here is where the power's coming in, part of Seco cable splice. All right, here's the cable splice. It's incoming high voltage service from ComEd manhole. So we're coming in at 12 kV, right? 12,000 volt cables. From there, we come into the main Seco vault. That one we were not able to get into. The one we were in was up on the top floor, right here. We were in this one. But this is basically my entire building's electrical distribution on one sheet of paper, allowing me to easily trace back and find where different loads are being powered, simply because there's multiple layers of protection. We're always most just familiar with the most closest local disconnect for a piece of equipment, but because of the multiple layers of protection, if something were to fail in between, you would definitely want to know where the hell to go in order to remedy that situation. All right, next we're going to talk about building emergency power. So we're gonna go and take a walk down to my generator room. And we'll look at the generator and talk about transfer switches. All right, we're gonna step into the generator room. Got a couple of fans for intake air. This is my generator here. So according to Chicago Building Code, it's a requirement for both old and new buildings to have emergency generator systems. Article 700 of the code is going to detail the system type, depending upon the building's use, and the basic requirements for all installations. Okay, this particular generator, go around to the nameplate, gives us all pertinent information. 938 kVA, which is basically kilovolts times amps or watts in general. Okay, so it gives you the maximum for which it would be able to output, and then of course you need to multiply that times about 80% due to power factor to give you your wattage. So if you look, it'll tell you 938 kVA, but only 750 kilowatts. So if we were to basically do that math, 938 times 0.8, it's going to give you 750. Okay, so this is a 750 kilowatt generator, which fairly decent, but relatively tame. I worked at a data center prior to coming here, and we had 6 2,000 kilowatt generators wired in parallel. It's the day tank, so there's fuel storage that is located under the planters out on the sidewalk on Huron Street. There's a pumping room down a few floors below that will pump up to this day tank to maintain a certain amount of fuel so that this generator could run uninterrupted. We have 8 transfer switches that are located in this building that will send signals to this generator should there be a failure in power. We will look at those in a second. Let's just talk about general maintenance. Typically we want to come in here once a shift, just do a visual inspection, check for leaks, check the battery levels, make sure. Here's the information for the battery. We've got leak detection, so we've got leak detection going around the entire base and perimeter of the generator, which would sound out remotely should there be a leak of fuel or coolant. So we want to check coolant levels, oil levels, air filters need to be checked, water heater. This is the water heater here. You can actually hear it heating up water. So we want to keep the temperature going to the water jacket of this generator nice and warm, so in the case it needs to start up at any time, it's pre-warmed and ready to go. One thing we like to do is once a week we'll come in here and we will give it a no-load test. Here's our walk-around inspection, check the belts, coolant system, black heater, air cleaner, all that stuff. We fill out the log and keep a record of it. And then annually we will have our transfer switches checked out, and we'll actually transfer a load over automatically and just see how this thing picks it up and works, make sure it works properly. All right, let's go into the electric room right adjacent to it. This is the switchgear for the emergency generator. It's got overcurrent protection, and then it's got the fused buckets that connect to the feeds for the different transfer switches, fire pump, and all the other loads that are associated with it. Turn around here. Here's the normal feed for a couple of ATSs, automatic transfer switches, which are located in this room. Let me go around this way, make it a little bit easier to see. All right, ATS 7, ATS 6. Normal feed from ComEd. And basically what these transfer switches would do is they're gonna monitor the power that's coming through the normal feed, okay? And in the event of a power failure, these switches will be able to send a start signal to that generator that we were just looking at. All right, the generator would then be able to ramp up the speed and take on the loads that these switches are connected to. So also these switches will have the availability to transfer those loads to the generator once that generator is up and fully operating. Transfer switches can be standalone units such as these that you're seeing here. They could also be integral devices which are mounted within the switchgear, switchboards, or panel boards as part of a building's distribution system. Transfer switches can come in a couple different configurations. These are open type transitions, which means they are break before make. They will not close until they open up from the utility power source. Another type is a closed transition, which is a make before break, where it will close while it's still connected to the utility feed. There are also certain situations where you could have a parallel feed. You could be feeding from your generator and ComEd utility at the same time. All right, that's about it in here. Let's continue on with our field trip. Next, we'll go into my chiller room. I'll show you how a chill water plant looks, and we'll talk a little bit about the operations up there. God bless America. All right, we're gonna head down the hall here, walk into our chill water plant. First thing you'll notice right outside the door, we got scuba, self-contained breathing apparatus in case of emergency or refrigerant leak. You'd want to put that on before having to enter this space. You also notice there's a indicating lamp, a flashing light, and an alarm. So for leak detection, that's connected to a leak detector in there. And then there's also a push button for emergency stop. It'll start the exhaust fan and it will automatically shut down the chiller. Condenser water pumps, chilled water pumps, the chemical station, controls for the chemical feed, emergency eye wash. Also has a little air horn, so in case somebody gets some chemicals in their eye when doing some testing, run over here, press down on the paddle, get some water in their eye, and it'll send out a big air horn so to alert anybody in the area. Extinguishers. You'll notice extinguishers are everywhere. One of the things you'll be asked on your quiz is what classification of fire extinguisher is used for electrical fires. Here, this is an ABC model, so it's able to do all three. A, which is your typical trash, wood, and paper. B, liquids, grease. And C, electrical equipment. So C is the correct answer for that question on your quiz. Pre-fill station, this just keeps the water level in the chilled water closed loop at the proper capacity. I'm doing a little work on this chiller here. Got it all tore apart. Here's the starter, and you'll see there is lockout tagout on this motor control. Okay, we don't want anybody accidentally turning on the power when the motor has been removed. The motor's gone. The motor's gone, and there's the open connections to it. So we definitely don't want anybody accidentally harming themselves. So these are both 650-ton York YK low pressure. So they operate in a vacuum. We're using R11. Never really converted. This building was built and all this equipment was installed, what, 89, 90. So that was right around when the EPA was railing against refrigerants, and that's when R11 started to go by the wayside. But what we decided to do, since our equipment was so brand new, rather than retrofit, we said, hey, let's fucking buy a shit ton and store it. So each one of these containers holds 1,000 pounds of R11. So that's 4,000 pounds, plus each machine holds about 850 pounds. So I've got enough R11 here to last a lifetime. All right, but back on the theme of electrical distribution, on the other side of this wall is a switchgear room. From that switchgear room comes and powers in this MCC, this motor control center. Okay, so motors are, of course, the most common loads requiring simple and complex control. And an MCC combines individual control units into standard modules that make it really easy for troubleshooting and servicing motor control circuits. So you can see all these individual buckets, as I call them, or modules. They just snap right into place. This is just a regular, there's bus bars back there, and they just snap right in there. And this one I propped open already, so there's another lockout tagout. That pump is not operable, so we've We've got it locked out. All right, so we open this up, and we've got everything in here. We've got transformer for our control, low voltage control. We've got our high voltage. Here's our motor starter. You can see we've got the reset there, so we've got overload protection. We're doing some monitoring. It's just current sensing device wrapped around one of the legs, B phase. So when this pump is activated, this is a pump? Yeah, it's for the condenser pump number 2. So when that pump comes on, that little device is going to sense current, and it will then send a signal to the building automation system to let us know that yes, the pump is actually running. All right, that completes our field trip for today. Hope you enjoyed yourself. If you have any questions, we'll be going live shortly, and please do ask. Also, just to let you know, as a part of this field trip, the link for discussion board, there are some questions that I would like for you to answer as homework. All right, see you in a second. Bye.